So I'm going to talk to you about Docker, which is an open source project which we released a few months ago. And it's a portable container engine. I'll talk about what that means. We've released quite a few open source projects at DocCloud. It is kind of a regular thing we do. But Docker is pretty special because almost immediately it got a lot of buzz. Right? People got really excited about it. And we didn't really expect it. We thought it was great. I personally am really excited about Docker. I think it's probably the most important project I've worked on. But because of the buzz, because of the excitement, I get a lot of questions. Right? People come to me and they say, "What the hell is Docker in the first place? I heard about it. I don't get it. Why? What's the big deal?" And since it's all about containers, I also get this other question, which is basically, what the hell is a container? Why should I care? And since I get that question a lot, in the beginning I would just demo Docker. That would be my presentation, just get a terminal and show it. And I thought, okay, let's take some time and talk about why I'm excited about it, why I think it's a big deal. And it is a big deal. I'll start by saying that. And I think containers, the concept of containers and the implementation behind it will be a big deal for all of us. I think it will affect the way we work, the way we create software, the way we distribute it in big ways in the coming months and years. And I think that's really exciting. So that all has to do with the problem of shipping software, specifically moving it from machine A to machine B. Whenever you're getting your code to work on machine A and machine B in the same way, and you're making an effort to know that it will behave the same way in both machines, you're shipping. And that's a primitive that we use all the time. And the problem is, we want it to be reliable, we want it to be automated, and a lot of times it's not. And so, examples of what I mean by shipping is, if you're sharing your development environment with a colleague or a contributor of your open source project, you're shipping, right? If you're deploying from your development machine to a staging server, you're shipping. Same thing if you're scaling out from one server to multiple servers, then you're shipping the same code to lots of different servers. And again, if you're migrating from one hosting provider to the next, or you're going from a private cloud to a public cloud, et cetera, moving into a new data center, again, you're shipping the same code to even more machines. And again, you hope that it behaves the same way, and hopefully you can do that in some sort of reliable, automated way. Otherwise, your life becomes really difficult. And that's the problem. Our lives are, I think, really difficult right now because that stuff is way too hard. It's really hard for a developer to get his code, all of it, to run reliably on all these machines that it has to run on. And the reason, I think, is that our applications got really complicated. At some point in the last few years, our software stacks started looking really, really complicated. I tried to make a drawing of that. But it used to be this really nice, simple stack, and now it's a service-oriented architecture with loosely connected components that interact with each other over the network. You may have all sorts of different languages working together, software components that you don't even know what language they're written in. You just have to use them. So you've got this really complex software stack, and it's running on an increasingly complex hardware infrastructure, right? You're developing on a VM on your laptop. You're moving that out to a staging server. The whole point of cloud infrastructure is that you can have more machines more easily, right? You make an API call and boom, you got a server. Now increasingly we're seeing organizations deploy on private clouds like OpenStack and then on EC2. Increasingly we're seeing companies spread out loads across multiple hosting providers. So what that means is the same software stack that can be pretty complicated to ship in the first place, now you have to ship more and more and more. So the difficulty is multiplied. And so I threw together an example of what that stack might look like to be sure we're talking about the same thing here. But a typical application this is an application I've seen. It might be a static website hosted on your own version of Nginx, a Ruby on Rails front end, a REST API endpoint that's written in Python using Flask, that sends jobs to a Redis queue, which is consumed by another Python worker using Celery. And that worker may have all sorts of special libraries built in to do special work. In this case, it was FFmpeg. And so the list goes on. That stack just kind of sprawls out. And as a developer, all of it is now your responsibility, right? These components use different languages. If you're using Hadoop for analytics, that's Java, so you need to figure out which version of the JVM you want, which system libraries you're going to depend on. Every time there's an application server, you have to pick a version. Eventually, you have to pick patches. You have to tweak the configuration. And all of that, that's your application, the whole thing. And then, again, that's going to move around from machine to machine. Soon enough, your customers are going to say, hey, I love that software, but I don't want to mutualize share a version of it. I want to run it on my own private servers. Can you give me an appliance? And again, you have to ship it. And so what you end up having to deal with is a sort of a matrix of every software component in your stack multiplied by every element of your infrastructure that it has to run on. And every intersection of that matrix has to work. If it doesn't work, something's going to break, right? You're going to test on Python 2.7, and then it's going to run on Python 3 in production. Usually it's the other way around, but and something weird will happen. You'll rely on the behavior of a certain version of an SSL library, and another one will be installed. You'll develop, or you'll run your tests on Debian, and production is on Red Hat. All sorts of weird things happen, and the underlying hardware properties are not always the same, right? The network topology might be different. The security policies might be different. Storage is different. Everything's different, basically. Yet somehow the same software has to run everywhere. So how do we deal with that? And how do we fix the current situation caused by this matrix, which is basically a very brittle, very labor-intensive process? How do we fix it? Well, the first thing we can do is look for examples of other people who had the same problem before and fixed it. And we happen to have such an example in the shipping industry. So the shipping industry obviously is in the business of moving physical things across the world from point A to point B. And obviously it's been around for centuries. And for the longest time, it actually operated in a way similar to the way we ship software, right? So you had all sorts of physical goods, furniture, boxes, barrels, bags of stuff, et cetera. And then you had the infrastructure necessary to ship it. So you had boats and trains and cranes and warehouses and all of that stuff. And the process of shipping something, let's say I want to ship coffee. I've got bags of coffee. To get it shipped, I actually have to worry about all sorts of intricate details about how it's going to be shipped, right? Is it going to be shipped along with a piano, and is the piano going to be sitting on the coffee beans, crushing it in the process? Does the staff in Rotterdam that I'm going to employ know how to handle bags? Will some of them be lost, right? So every step of the way, you've got this combination of infrastructure for shipping and things that are being shipped, and you just got to figure it out as you go, right? And the result, again, is this complicated matrix and a very labor-intensive and unreliable process. And so that was the way it was for a long time. And then one day, in the 1950s, a few people got together in the shipping industry and agreed on a standard box. They agreed on the dimensions, they agreed on the weight, they agreed on the way the doors would work. So they agreed on a format, and they agreed on a standard set of operations. Basically, they agreed on an API and started using it. And so the shipping container was born. And it's a pretty ugly box. I think everyone knows what that box is. But that box literally changed the world. They changed the shipping industry, first of all, because what it enabled was separation of concerns. All of a sudden, if I want to ship coffee, all I have to do is put it in my container any way I want, with other stuff if I want to, it doesn't matter. Then I close the door, I seal it, and I put a tag that identifies the container. And from that point on, getting the container to the other side of the world is no longer my problem. My infrastructure provider will take care of that, and all I have to do is wait for the container to show up on the other side. I break the seal, I open the door, and it's my problem again. In between the two, I don't need to know what happens. I don't need to know where it goes through, what harbor, what infrastructure. It doesn't matter. And conversely, the infrastructure provider does not have to worry about what's in the box, right? They have standardized cranes, standardized boats, standardized trains, et cetera. all of which are interchangeable, all of which can deal with any container in the world. I think there's something like 50 million shipping containers in the world today. Every single one of those containers can be loaded by the same cranes onto the same trains, the same boats, etc. And that's actually very powerful because with this separation of concerns comes automation. And with automation comes reliability and low cost. And basically what happened is the shipping industry exploded. And by the end of the 60s and the 70s, there were so many ways to ship things to places where it was not practical to do so that marked the beginning of global trade, and it literally made the world smaller. Right? It's one of those few inventions that really changed the world very, very rapidly. And so this brings us to this embarrassing situation where it's actually the automation for carrying coffee across the world is better, more reliable than the kinds of tools we use to ship software between computers, right? I think that's pretty embarrassing. And so I think that it's important that we copy that idea and come up with a shipping container or something similar for software, right? Going back to my example from the beginning, if I'm a developer, I should have a standardized way to take any software component, put it in some sort of box, and then hand it to infrastructure providers and not worry about how it's going to be deployed, right? Separation of concerns. And the operations team in charge of infrastructure should be able to do all sorts of things with that container without worrying about how I built it, what language I used, all of that stuff. Now, the next question is, why has it not been done before? After all, it sounds a lot like sandboxing, and you guys write code, so you're thinking, well, I write Java, and I use jars, right? Isn't that a container? Or I write Python, I use virtual env. Isn't that a container? And so, yes, those tools enable me to sandbox my code. They enable me to put something in a container, but I can't put everything in it. In other words, the sandboxing is incomplete. And I think very quickly when you keep working on an application, you realize I can put all of my Python dependencies in the virtual env, but I can't put my system libraries in it. And there's always a dependency at some point that goes outside of that box, right? Especially in the modern application environment. The whole point is that you can use components from this huge community of developers writing in all sorts of languages, right? We're supposed to be polyglot. And so what's the point of being polyglot if we can't reuse each other's code? So these tools are great, they're practical, I use them every day, but they're not sufficient. Okay, then option two, what about VMs, right? If a Python package is not enough, if a jar is not enough, then let's just take the whole machine, let's put the software in it, and let's just share the computer along with it. That way, we are guaranteed to have the same context for everyone. And that is actually a very good idea. And I believe the only way to share software in a truly reliable, repeatable way is to ship the whole system with it. Because really, the system is part of the application. Your choice of distribution, your choice of system libraries, all of those choices, even if you didn't make them consciously, maybe you just used the system that was lying around there, that is affecting the behavior of the application. And if you swap it out, things will change. The problem, though, with virtual machines is that they bundle too much, right? You do want the whole system, but you do not want, as a developer, to package things like a whole hard drive, right? A whole virtual set of processors, of network interfaces. You don't want to be deciding as a developer, this is how storage is going to work for this application everywhere. This is how networking is going to work. This is how much RAM there's going to be. This is what the kind of processor, that's the kind of processor that you're going to use. You can't do that because then you're breaking separation of concerns. The infrastructure provider is not free to implement, to make those decisions based on the current machine, right? So to take the metaphor of shipping containers, the shipping company should be free to choose the crane. It should be free to choose the boat. The fact that I'm giving them coffee bags to ship doesn't mean I can tell them which crane to use. That's the whole point. So another problem of virtual machines is they are extremely heavy. Anyone who's tried to simulate a whole stack of maybe 10 components on their laptop by booting 10 VMs probably agrees with me, right? If you've ever tried to do computationally intensive work on a cluster of VMs, you also agree with me. There's overhead, it takes CPU, it takes RAM, it takes a long time to boot. It's a machine. So it's not practical as a unit of software delivery. Okay, what other options do we have? And this is where the set of discoveries that lead to Docker come into play. There is a way to get the best of both worlds. And the best way to describe the best of both worlds is I want to sandbox the entire system so that as a developer I know everything that's going on. I have a guarantee that what I ship is going to be repeatable. But I don't want to ship the machine details because that's too much. And I don't want the performance hit of a VM. So that's kind of the pipe dream. And it's been the pipe dream for a long time. And the good news is now it's possible to have that and to have it be so fast that it's actually scary how cool it is to use. And that is all thanks to the Linux kernel and other kernel hackers in the world that have finally implemented namespacing that works. And what that means is you can now, using a modern Linux kernel, isolate any process from the others and basically make that process believe that it has actually its own VM when really it doesn't. And that includes isolating the file system, the network interfaces, memory, resource access, the whole thing. And it works in the Linux kernel. It works well enough to run in production. And that's what we've been using at .cloud for a long time, testing it, dealing with its quirks, and now it's ready. And the result is best of both worlds. So enter Docker. Right? The reason Docker exists is that these capabilities, which we did not develop, right? The countless developers of the Linux kernel did. They are raw capabilities. They're not readily usable by everyone. It's not the point, right? The point is to use them as building blocks to build something else. So what's missing is a standard container format that developers can use, and that's what Docker does. So we do three things. The first thing we do is we define that format. And by the way, this is our new logo. I just found out about it today. We did a contest. These little boxes are shipping containers, obviously. So we define the format to standardize how to ship software, right? And then we give simple tools for a developer to build his source code into a container, regardless of the language, regardless of the build tool, regardless of all of that. And separately, we give the ops team, the guys running the infrastructure, simple tools to take that container without having to know what's in it and then run it. And run it, hopefully, on as many machines as possible. So we're working very hard to make Docker run on as many machines as possible. So that's how Docker works in essence. One thing we've tried really hard to do, is not come in and say, hey, if you want to use Docker, you've got to stop using these other tools, right? And that works for developers and ops. We're not telling developers, you got to learn this new packaging system, you got to learn this new, stop using make, stop using pip install, stop using jars, use this thing again, learn it, throw everything out. We're not saying that. And we're not telling the ops guy, forget about Chef, Puppet, and all that stuff. Forget about your current system packages. What we're saying is, here's an ingredient which is very lightweight. It's designed to not get in the way. It's designed to improve your existing tools. And if you integrate it into your tools, then all of a sudden things will start getting really awesome. And you'll have all these nice properties. Specifically, you'll be able to ship software from machine A to machine B reliably and automatically, which is the whole point. So it's open source. It's written in Go, which has the nice property of compiling down to a static binary. And you can drop it into any server, and it just runs. It has all sorts of nice properties like that. Really, you can think of it as the result of the last 5 years working at .cloud, trying to figure this problem out, and finally reaching a point where we feel like we found a good solution that is simple and elegant enough to share with everyone. And that's what we're trying to do. So I want to encourage you guys to check it out if you're interested. The thing we need most right now is feedback. Docker just reached version 0.4. It's very young. It doesn't work perfectly yet. We need more people to try it, break it, find bugs, adapt it into their own workflow,